Hi, everyone. Welcome to my little, somewhat abbreviated makeup for last Thursday's lecture, the Imelda Interrupted lecture. I know not everyone could get there, and the people who were there were wet and a little distracted, so I'm going to do my best to summarize where we are. Hopefully, in addition to watching this, you will, if you did not make it to the lecture, you'll try and get the notes from somebody because they might be more complete than what I'm about to do here. So if you recall, we discussed, last time we discussed the thermodynamic square as a mnemonic, right? What I had done is I had shown you a bunch of techniques involving partial derivatives that are part of sort of a general problem-solving strategy, and now we're going to work through a few examples. And one of the things we learned is basically the properties of nice functions, the idea that underlying all of our thermo understanding is this of simple systems is this function S, the entropy that is smooth and continuous and multiply differentiable, and the fact that everything has to be mathematically consistent for that and its Legendre transforms of different kinds establishes a bunch of relationships that have to be obeyed between derivatives of different thermodynamic quantities. And so this is our little copy of the thermodynamic square here. Good pupils have studied under, as spelled with an E, very fine teachers. All right. So just bearing that in mind, I'm going to introduce a few commonly appearing thermodynamic derivatives. And these are special and have their own names because they're the kinds of things that you could actually measure in a lab, particularly in the 19th century. And it's convenient to put things in terms of these measurable quantities. That's the really remarkable take-home message that we're going to find here, is that the fact that there's this underlying mathematical framework means that we can establish very, very general relationships between things that can be measured in the lab, where at first glance it's not at all obvious that these things should be related to each other. So one of them, which we've talked about before, alpha is the thermal expansion coefficient, and the thermal expansion coefficient is defined as 1 over volume, partial temperature at constant pressure. This is the fractional change in volume with temperature, and remember I mentioned before that the thermal expansion coefficient for something like brass or some other metal is typically parts in 10 to the 4, and if you have floppy polymers, the thermal expansion coefficient is more like 1%. A related quantity, and again, we use beta to mean many things in this class, unfortunately, because of convention. I will put the little subscript T here to remind you that it's an isothermal quantity. It's something that happens with temperature held constant. Beta is the bulk modulus. This ends up being related to the speed of sound in materials. And beta sub T is defined as negative the volume, partial pressure, partial volume at constant temperature. I'll say more about that in a moment. Another quantity that shows up a lot is kappa sub T, which is the compressibility. And the compressibility is defined as minus 1 over the volume, partial pressure at constant temperature. So you can see that, assuming that derivatives are nice and behave well, that kappa is basically 1 over the bulk modulus. Now, how should you think about these things? So the compressibility, this is the fractional change in volume as you squeeze on something, right, with a known pressure. So if I crank up the pressure and the volume goes down, I will have a positive compressibility. That's what this negative sign out front means. Flipping it around, basically, when you talk about the compressibility, the idea here is that you're applying a pressure and you're seeing how the volume responds to it. With the reciprocal, the bulk modulus, it's more like I'm changing the volume and I'm seeing what pressure is generated by the material in response to that, right? So these are clearly related things, and as I said, they're reciprocals when these derivatives are nice and well defined. All right. So what we're going to do, pardon that pause, what we are going to do is we're going to look again at our expressions for the heat capacities. We had done a derivation that was assuming the ideal gas, right? And now we're going to do a little bit more of our derivative manipulation stuff. And we are going to see that instead of doing the ideal gas, we are going to do the more general case. So what we're going to do is assume constant n, constant particle number. So I'm going to basically not worry about derivatives with respect to particle number for the moment. And we are going further than that. We are going to oh, never mind. We'll get there. So we're going to assume constant n, and we're going to the question we're going to ask is, what is the relationship between Cp and Cv? And recall, Cp is defined as T partial S partial T at constant pressure. Right? That's our definition of the heat capacity at constant pressure. Cv is defined as T partial S partial T at constant volume. So knowing that, it makes a lot of sense to do the following. We will start off. We're gonna assume that the variables we're gonna start caring about here are temperature and volume. We're gonna go from there. So we're gonna say ds is partial S partial T at constant volume dt plus partial S partial volume at constant temperature d volume, right? So this is basically just assuming that our independent variables are temperature and volume, and of course we're suppressing particle number, so we're not worrying about that one. And we're going to use our chain rule for partial derivatives. We're going to consider variations in temperature that happen at constant pressure, right? So if we do that, then I can write, you can either think of it as applying the chain rule for multiple variables, or cosmetically, in a completely non-rigorous way, it's going to look like I'm dividing through by some small differential dt and considering it to happen at constant pressure. So if we do that, we have partial S partial T at constant pressure equals partial S partial T at constant volume plus partial S partial volume at constant temperature from before, partial volume partial temperature at constant pressure, right? So we've done our little variable manipulation. And so if I multiply everything through by, let me change colors for a second. If I multiply everything through by temperature, right? Then I can write Cp equals Cv, right, from our definitions, plus temperature, partial S, partial V at constant temperature, partial V, partial T at constant pressure. All right, so I've just rewritten that on a fresh slide, and what you can clearly see is something we're gonna take advantage of. We're gonna use our Maxwell relations to get rid of this partial derivative. So partial S, partial V at constant T turns out to be the same thing as partial P, partial, pardon me, my software is being very annoying. Partial P, partial T at constant V. So this, we're going to, like I said, we're going to replace this with partial P, partial T at constant V. All right. And so, again, we're also going to plug in that this thing here is V times alpha, our thermal expansion coefficient. So that being the case, we can rewrite this Cp equals Cv plus T, partial P, partial T at constant volume, times V times alpha. This is so far completely general. We have not assumed anything about the materials. This should hold for any simple material, solid, liquid, gas, any of them. All right? And let me find my appropriate page here. Okay, so then we're going to do something more interesting. We are going to remember that we can rewrite our partial derivative, partial p, partial t at constant v. We're going to use another of our differentiation identities, partial t, p, partial t at constant v, is negative partial v, partial t at constant pressure over partial v, partial pressure at constant temperature. Right? We actually went over that in our, this is one of these ones where we proved it about, partial z, partial x at constant y, and so on. We went and did this. So if I plug all of that in, right? If I use this identity here and I plug all of that in, now I end up with my final statement here: Cp equals Cv plus temperature times volume, and it's going to end up being alpha squared over kappa, right? This is the relationship, the general relationship that has to hold between the heat capacities for any material. You can go into the lab and you can measure temperature, you can measure volume, you can measure thermal expansion coefficient, you can measure compressibility by doing experiments. And if you are, if you're just doing this carefully for a simple material, you will find this relationship has to be obeyed. That's pretty damn amazing, the fact that there is complete generality about this. And it all comes down to the fact that deep down under everything, the entropy exists and is the basis for our formulation of thermodynamics and has a bunch of nice mathematical properties. Okay, so let's start actually talking about thermodynamic processes, because this is the kind of problem that often is asked on homework, and sometimes it's asked on exams. And the difference, a process takes you from some initial condition to a final condition, and processes are components of what you would call a thermodynamic cycle. A cycle is a special example where whatever system you're considering about, you go through a series of processes and end up back where you started. And so cycles are where you start talking about things like refrigerators, or engines. With an engine, you run some kind of a cycle, and then you ask, all right, I got my system back to where I started. Did I get work out of my system in exchange for doing something with heat? Refrigerators are the complement of that. I can run some series of processes, get back to where I started, so in principle I could do it again. And I can ask, how much heat did I move? How much energy did I move in the form of heat from, say, the cold side inside my refrigerator to the hot side outside my refrigerator, right? And how much work did it cost me to do that? So all of these things, I just want to get you used to thinking in terms of processes and cycles. So we're going to consider a series of different processes, right? The first two are ones we've already seen before, so it'll be quick and easy. So we're going to think about the isothermal expansion. And in fact, so first we're going to consider the general case, right? Actually, I'll take it back. First, we're going to consider just an ideal gas. All right. So isothermal just means constant T. All right. Now, for an ideal gas, E is a function of only the temperature and the particle number here. I told you that. We will eventually derive it more rigorously. But the bottom line is, and again, this only applies for the ideal gas, constant T implies constant E for the ideal gas, right? So then we can talk about our expansion, and maybe the question we're really asking is how much heat, how much energy in the form of heat was transferred to or from the gas to go from volume 1 to volume 2 at constant temperature, right? That's the question we're really answering. And again, we're doing the ideal gas case. Okay, so dE equals TdS minus PdV. We know that. That's our first law of thermodynamics. And again, we're suppressing the particle number piece. And we know this has to equal 0 because we just said there's constant energy, right? So if that's true, then if this is the heat added, the energy added in the form of heat, and this is the work done on the gas, then the sum of these things has to be 0, which implies that the heat added total must equal the integral of P dV from V1 to V2, right? So what is that? So P equals NKT over V for the ideal gas. So then we have that total energy added as heat must equal integral P dV from V1 to V2, which is integral N K Boltzmann T over V dV from V1 to V2, right? And that is, pardon me, that is just N K Boltzmann T natural log V2 over V1. If V2 is greater than V1, then total heat added must be greater than 0, right? It costs energy to expand the gas and yet keep the temperature fixed. Okay? So fine. So we've answered the question. How much heat was transferred to the gas if we go for, well, the heat is transferred to the gas going from V1 to V2 if V2 is greater than V1. Okay? Fine. So that's the isothermal expansion. The next thing we can do is the adiabatic expansion, right? So this is adiabatic in the thermodynamic sense, which just means no energy transferred as heat. I'm trying to be very careful about my phrasing. All right. So if it's reversible, this is a big deal. Reversible meaning I can have some macro way to undo it, undo the process. Then S equals constant, right? If it's reversible and there's no heat transfer, then S has to be constant. So we'll do an irreversible example in a second. But now the question we're going to try and answer, okay, so we're going to do an adiabatic isentropic expansion from V1 to V2. And the question we're going to ask is, what is the change in energy of an ideal, again, we're going to do the ideal gas case. Right? So what do you think is going to happen? What's going to happen is if we're really expanding the gas and we're not adding any more energy, then we know that the gas should cool off. The temperature should go down as you expand it because you're basically letting the gas do work. So if you think of this as a thermally insulated, here's my gas inside of a cylinder and here's a piston and I'm going to let the gas push on the piston. The gas is doing macroscopic work on the piston and no heat is being transferred in. So the energy of the internal energy of the gas has to go down, right? Because we're to mechanically move this piston, we're stealing kinetic energy from the gas molecules. Okay, so what can we do here? Well, we have TdS is 0, because S is constant under these conditions. And that has to be dE plus P dV. And for the ideal gas, here's where we're going to use the ideal gas part. We know that P dV plus V dP has to equal N K Boltzmann dt, right? And also for the ideal, so this is just taking variations of the ideal gas law. And also for the ideal gas, and again, just take this as something that we should believe, right? We have not derived it rigorously yet. dE is just going to be CV dt, right? Because E is only a function for the ideal gas, only a function of the temperature and the particle number. Okay, so if you combine those things, what are you going to end up with? You're going to end up with, starting with the TDS equals 0 piece, you're going to have 0 equals CV over NK Boltzmann P dV plus V dP plus P dV, right? You're just grabbing all the terms and combining them together. And if we multiply through and rearrange things, you're going to have that 0 equals CV times the volume times dP plus, and in parentheses, we're going to have CV plus NK Boltzmann P dV. And you may recall this, for the ideal gas case, turns out to be CP, right? So if that's right, then we're going to end up with dP over P plus gamma. Gamma is defined as CP over CV, our ratio of heat capacities, plus gamma dV over V. That all has to equal 0. And so this is our derivation that we did last time. It basically shows that PV to the gamma equals a constant for this adiabatic, isentropic, ideal gas case, right? And if we also know the ideal gas law, then this implies that TV to the gamma minus 1, minus 1, is a different constant, but still a constant under this process. And so if that's the case, right, then that means that T1 V1 to the gamma minus 1 has to equal T2 V2 to the gamma minus 1, right? And so then delta E, which is the thing we care about, is going to be CV times T2 minus T1. And so we can just plug stuff in. And what are we going to find? It's going to be CV T1 times V1 over V2 to the gamma minus 1, all minus 1. All right. And this does have the right sort of behavior. If V2 is bigger than V1, then this ratio is going to be smaller than 1. Gamma is greater than 1. This ratio of heat capacities has to be greater than 1. So this whole thing here, this whole term is going to be less than 1 if V2 is greater than V1. And that means that the thing inside these parentheses is going to be negative, and we will, in fact, find that the energy of the gas goes down by some amount if the system is expanded, right? And we actually know how much. So, okay, so what processes have we done so far? We have done isothermal expansion, and we did the ideal gas case. We did what happens when there's an adiabatic isentropic expansion, right? Let's do another kind of expansion now, another kind of thermodynamic process. We're going to do vacuum expansion, which what we're going to do is we're going to imagine having a gas in some high pressure environment. Here we go. Here's our gas, and we have a valve. And we are going to open that valve and go from V1 and T1 into some final total volume V2 and some final temperature T2, okay? The deal, though, is that this starts out as vacuum. This stuff out here starts out as vacuum. All right, so this kind of vacuum expansion, this kind of expansion where you're taking a gas and you're putting it through an orifice like this is called throttling. Just historically, if you throttle an engine, if what you're doing is you're squeezing some gas through some sort of a pinhole or something. All right. So this is a bit special because you're expanding into vacuum. This is not reversible. There is no way to run things backwards by just moving back some macroscopic coordinate or something. You can't move a piston back or something and get all the gas to go back in the smaller volume, right? So it's not reversible. And so what does that mean? It means delta S has to be greater than 0. And that's sort of intuitively obvious. The number, if you think of S as being related to the number of ways you can arrange the molecules, clearly there's a heck of a lot more phase space available once you've expanded into the vacuum than before. So even though there is no heat transfer in this case, but delta S is greater than 0 because it's irreversible, right? This is a bit of a subtle point. Okay, so if there's no heat transfer, the other thing you have to remember, so that's one point. The other thing you have to remember is there's no work done on or by the gas. Again, how should you think about that? Well, these gas molecules, they don't, nowhere in this process are they transferring their energy to some other system, right? So they're not pushing on a piston or something. So there's no work done by the gas. So if that's true, then that implies that the energy of the gas, must be constant, right? There's no heat transfer. There's no work. So the energy has to be constant. And so the thing we're going to care about is figuring out what these final conditions are. So what we need to know basically is what is T2 under these circumstances, right? Okay, so this is an example of a problem where we know the endpoints, even though it's irreversible, and so therefore we can't divide it up into a bunch of little quasi-equilibrium things along the way. We know the endpoints. The start is in equilibrium at T1 and V1. The finish is in equilibrium at some currently unknown T2 and some final volume V2. But we're in equilibrium in both cases, right? So what we need to do is figure out what we need to do is to basically find, in principle, we should find the energy at T1 and V1 for n particles. We should find an expression, ideally, for the energy at T2 and V2 and set those two things equal to each other because the energy has to be constant and solve for T2. That's kind of what we want to do. So how would we go about doing this? Well, remember, in equilibrium or near equilibrium, right? We have our first law. We have that dE equals TdS minus PdV for fixed particle number. We can, again, temperature and volume are the things we care about. So this is going to look like a rehash. ds is partial S, partial T at constant volume, dt plus partial S, partial volume at constant temperature, d volume. We know from before, from our Maxwell relations, that partial S, partial V at constant T is partial P, partial T at constant V. I apologize if you can hear my dog sighing in the background. Okay. So, again, we can multiply everything through by temperature if we want. And in that case, we, right. So we can, yeah. T, right? Okay. So, fine. So we've done that. And that means that, what do we have? We have that we know we have an expression now for TdS, right? So we know what TdS is, so we can substitute it into the first law. So we're going to take our expression for TdS, which is all the stuff on the right-hand side, and we're going to plug it in up here. So if we do that, we can then say dE equals CV dt plus T partial P partial T at constant volume dV minus P dV, right? I've just combined all of this stuff, and in fact, I can make it a little cleaner looking. I've got T partial P partial T at constant V minus P all times dV. All right, so that's all true and completely general. And what in principle we could do here, right, is we could integrate this up. And if we did that, we could find E as a function of T and V and N. And we could basically solve, we could set the energies equal and solve, and we'd be all set. Right? Okay. So one of the right. So the one remaining thing I want to point out, which we sort of covered once before, is this idea here that if we now do the ideal gas, so far we haven't assumed the ideal gas, but if we do the ideal gas, what would we find? We would find that T partial P partial T at constant volume minus P is 0, right? So we would then find that the energy is only a function of temperature and particle number, which means we would find that T2 equals T1, because the energy only depends on temperature. We said the energy was constant, and so therefore for the ideal gas, with the vacuum expansion, we would find that T2 equals T1. Okay, now we could do something a little different. We don't have to assume the ideal gas. We could assume the van der Waals gas, and in the case of the van der Waals gas, things are a little bit more complicated. I will instead of going into this in any detail, though, I will pick this up first thing on Tuesday. We'll do something very quick and very brief on Tuesday with the van der Waals gas, and then we will do another kind of expansion, and then we'll talk a little bit about cycles, thermodynamic cycles and engines and stuff, because that's really good, meaty thermo stuff that you all should know as literate scientists. All right, so this is sort of the slowed down, no, sorry, not slowed down, excuse me, the slightly abbreviated version of what I did on Thursday. And hopefully you will all have a chance to watch it, and you can watch it again at your leisure, and we will pick things back up on Tuesday. Hope you all manage to stay dry in the storm. Thanks.